Welcome to this course on data assimilation. We are going to provide a very broad background about the theoretical aspects of data assimilation. Our first lecture will be on providing an introduction and an overview. I would like to start with the question, what is assimilation? The concept of assimilation in general conjures up various meanings in different disciplines. In biology, for example, the human, animal, plant body assimilates or absorbs food. So here the word assimilation refers to the process of absorption of food by living organism, be it human, animal or plant. So here assimilation refers to a biological process. Assimilation also happens within the context of sociology. Immigrants, refugees from one country, they try to rehabilitate in another country by assimilating into the prevailing culture. In this context, assimilation refers to the sociological process. As an example, United States is considered to be an example of social experiment. It is a melting pot of sorts where there is continuous assimilation of all cultures from all around the world. However, within the context of physical sciences and engineering, assimilation refers to the process of fitting models to data. So in this process, the key players are model, data, and the process of fitting data to the model. So this involves three different disciplines. One is science of model building. Second one is ability to observe nature, and the observations give rise to data. Data is available, models available, but we need to bring them together. This bringing together, that is the assimilation process. That process is also called fitting models to data. Looking from this perspective, data assimilation is a very broad and a vast discipline. It is very broad, it is very deep. We would like to develop a very holistic view by looking at various practices that go with different names, but the underlying process is always related to data assimilation. Recall the old saying, the whole is greater than the sum of the parts. So the process of fitting models to data, the process of various types of assimilation, these are all various parts that come to be called the science of data assimilation. The whole is much bigger than many of its parts. First, I would like to talk about data assimilation as a curve fitting or a regression process. The notion of fitting in data assimilation is the same as that is used in deterministic curve fitting or interpolation that is often used in numerical analysis. It is also intimately related to statistical regression analysis. To further understand the relation between data assimilation and other practices, we need to be able to introduce different classifications of models. Please recall, models, data, and the process of fitting are the three components. Now we are going to look into properties of various kinds of model that occur in almost all of sciences and engineering. Models in general can be classified into two types. Type 1 is called process specific model. Type 2 is called data specific models. Let us first concentrate on type 1 models. Here we understand the underlying scientific process that is at play. These are developed based on causality. If there is a force, there is a reaction to that. It is always a cause and effect relation. In sciences, many of these causal relations are nicely captured in the form of conservation laws. Here are some examples of models of type 1. The harmonic oscillator that describes the motion of a pendulum in a friction-free environment. The shallow water model that can be used to describe the motion of waves in the ocean. The primitive equation model that is the basis for many types of weather forecasting. Geostrophic vorticity equation in particular, one of the equations which is very generic and has applications. In particular, it's the basis for hurricane prediction. So you can see models come from various shapes and forms. Each one of them are developed based on fundamental scientific principles, causality based, process based. These are essentially statements of conservation laws. As opposed to these, the second type of model, they are called data specific models. Here there is no underlying causation, there is no cause or effect that is well established. All that we have is the availability of a bunch of data. These data are observations of Mother Nature. Given a bunch of observations of Mother Nature's behavior at various times, it is up to us to be able to mine the underlying information, and that mining is done with respect to finding the correlation between the data. This is also called correlation based or similarity based. These models are essentially empirical as opposed to based on physical principles. These models can be either an explicit model or an implicit model. For example, I have a time series. The time series could be value of IBM stock over each day, the maximum temperature in Bangalore each day, the unemployment rate in the state of Karnataka every month. This is an example of a time series. We would like to be able to build models for using these time series data to be able to predict how the unemployment will be in a year from now. What will be the maximum temperature in Bangalore in middle of January. These are called explicit models. These are empirical models. These are essentially based on correlation. Machine learning provides again lots of opportunities for model building based on data. Neural network is an example of a specific kind of machine learning process where we try to build a specific neural network to be able to undertake a specific task of being able to classify. The neural network models are essentially implicit models. You give an output, you try to tune the model until you get the required output. You probably may not be able to explain why and how, except that if you did the right thing, you can make it work. Again, these are data specific. For example, the time series model that is used for IBM stock price may not be the same time that can be used to predict tomorrow's maximum temperature in Bangalore or unemployment percentage, so on and so forth. So each one of these data set has to be looked at separately. For each one of these data set, we have to uncover the underlying serial correlation. Here I would like to make a statement about the definite need for correlation. If a collection of data are not correlated, means one does not influence the other. If one does not influence the other, we may not be able to predict anything at all. So ultimate aim in model building is to be able to predict. Once you have a model, I can pull the model solution forward to be able to make predictions. So correlation is a very fundamental attribute of data specific models, and it is using this correlation the model is able to extrapolate, make predictions. Pattern recognition is another example of explicit models that are again data specific. Now another dimension to data assimilation I would like to bring to forth. The development of type 1 models and data assimilation models, for these models are separate processes. For example, a physicist may try to develop a primitive equation model. An observation specialist may try to get data from satellites or radar. A data simulation person then comes into play to be able to understand the properties of the model, understand the data set, and to be able to bring them together. So model development and data simulation process are two separate processes. It is the data simulation person is the one who sits in the middle, who tries to talk to both the model and the data. The structure of the model in terms of spatiotemporal evolution, relation among the state variables are specified by the details of the model. Yet many of these models may have several unknowns. For example, in a primitive equation model, we may have an initial condition, we may have a boundary condition. Depending on the type of processes involved, different kinds of parameters may also become part of this equation. I know a certain class of primitive equation model helps you to predict weather in a particular situation, but to be able to initialize the model, to run the model forward, I would need initial conditions, I would need boundary conditions, I would need parameters. So models are specified modulo initial conditions, boundary conditions, and parameters. To be able to run the model forward, we need the values of these. And how do we get to know the values of these parameters? That is where we use the data. So in here, the goal of data simulation is to be able to estimate the unknown from the knowledge of the available data that is supposed to contain information about the unknowns. I would like to explain this a little bit further. For example, a quasi-geostrophic vorticity equation is often used to be able to predict the movement of a hurricane. But that is a very generic kind of equation. If I want to be able to use that model to be able to predict the movement of a hurricane, I need to know where it is today and what are the coordinates of that, what are the pressure differences, what are the various other attributes. So somebody has to fly planes into these hurricanes, they collect data, they bring the data to the office, so that tells you observations about the phenomenon. I understand the science, the physics behind the hurricane. We would like to be able to bring these two together in order to be able to estimate the unknowns, initial condition, boundary conditions, and parameters. Therefore, you can readily see data simulation is closely related to the classical estimation problem. This is fitting the observations of hurricane to the hurricane forecast models that was developed earlier. This aspect is related to estimation theory. There is another point of view one can take. Data simulation has also a lot in common with systems identification as used in systems engineering. In systems engineering, estimation of parameters of a system to maximize the performance is known as system identification or adaptive identification. So let us look at the picture here. This one is an engineering system. There is a physical plant. The physical plant may be a chemical plant, it could be an aircraft, it could be a ship, or it could be any kind of engineering device. It has input, it has parameters which are knobs that is meant to change the behavior of the system. For example, if this were to be a chemical plant, the input could be raw materials. The parameters could be the presence of catalyst, it could be temperature, it could be pressure, it could be concentration. So these are all various parameters that one can control. So the output of the plant depends on the physical properties of the engineering system along with parameters and the input. I would like to be able to understand the dependence of output of the input. So we try to express that relation in the form of a cost function. We would like to be able to maximize or minimize. If it is cost is always minimization, if it is profit it is generally written as a maximization, it's an optimization problem. So we would like to be able to change the input and the parameters in a feedback loop such that I try to maximize the functioning of this plant. This often occurs in many of the engineering systems. You can readily see in here data simulation is done online. A physical plant is operating, it provides an output that is a function of the input. I don't know what is the maximum output possible. I'm going to learn the maximum output by sequentially changing the input and the parameters in the loop based on a pre-specified criterion called the cost function. This often happens in all branches of engineering. Now let us come to physically occurring systems such as meteorology, such as geophysical sciences. There are observations of geophysical sciences we often do. The observations of geophysical sciences come from satellites, radars, balloons. Ships collect information, airplanes collect information, and these days we have ground based stations all around. Over the ocean we have lots of buoys. So observation comes in various shapes and forms. The observation contains secrets about the functioning of the nature. The modelers believe that Mother Nature behaves in a particular way. They encapsulate the behavior of the model based on their understanding in the form of process based models that we talked about. The process based models in general can be a dynamic model. If it is a dynamic model, it can be based on ordinary differential equations or partial differential equations. These models have initial conditions, boundary conditions and parameters. We only know the model describes the overall observations in some specific ways, but we would like to be able to fit the model to the data so that a specific model can be used to accommodate the specific set of observation to be able to generate predictions about a particular hurricane, a particular tornado, a particular naturally occurring event. So this is how we use the data which are contained in the observation and the model fitting model to data. So this is an alternate view. This is the view that often occurs within the geophysical domain, oceanography, hydrology, atmospheric sciences, volcanology and so on. Now I would like to talk about how data assimilation takes place in empirical models. In empirical model there is nothing. We don't have physics. All that we have is a bunch of data. So I have to use this data in two ways. So we have a twin task. One is to be able to build the model, and then once we have a general understanding of the class of models that we can use, then we have to do data assimilation on these models using the data. So let us look at the data mining part. The data mining part is the process by which I would like to be able to understand the structure that underlie the creation of the data. So what is that we do? We compute the correlations. We compute the similarity measures in a given data set. Based on the correlation we can narrow down a potential class of models to a small subset. As an example, in the case of time series, we may say we are looking at the correlation structure. If the correlation persists for a long time, that means it has a long memory. If the correlation comes down to low values very fast, if it decreases, for example, a correlation could be a correlation structure could be like this. Here the correlation does not decrease too fast. So these kinds of processes are supposed to have long memory. Another could be the correlation comes down to 0 very quickly. So the class of models for this is one kind of model, this is a second kind of model. There are guidelines to choose certain kinds of models for correlations of type 1, for correlations of type 2. Even here one has to contend with the orders of the model, but just by looking at it we cannot say this model worked better, that model worked better. So we have to be flexible, try to be able to have at least a couple of different ways of looking at it. So once we have narrowed down the choice of models, it is like having a barotropic vorticity equation. It is having a primitive equation. So we have to come to the same level as in the process based models by looking at the data to do data mining process. We will talk a lot about data mining a little later in this lecture series. in this introductory chapter. Now once the model is available, again in the case of time series models, the models are dynamic. Given any dynamic model, we will have initial conditions, we have parameters. To be able to pull the model forward, we need to be able to know the values of these parameters again. So once the set of models are selected, we can use the same data set to estimate the unknown parameters by fitting each of the models to the data. So now you can readily see, independent of the type of models, the process of data assimilation requires the presence of a model, the presence of an associated set of data, and then the process of fitting. That story must come pretty clear by now. So here there's an added difficulty in the case of empirical thing. In the case of process based models, for hurricane we know what class of models to use. For certain type of atmospheric motions we know what certain type of models to use. For oceanography they have a pretty good understanding what type of models to use. So a given process has associated with it the already understood class of models. In the case of empirical model building, models of types 2, there is no such clear cut association. There is no clear cut way to be able to decide this model will work better than that. So we have to always contend with a class of models. So within this context, the notion of model selection becomes a very important and a fundamental task. There are several methods one can look into to be able to develop and compare the quality of each of these models to a particular given situation, and we are not going to indulge into the model selection process. Those of us who are working in the empirical model building has to be cognizant of the requirement of being able to use very good criteria to be able to select good models for a particular given kind of data set. So now you have seen two aspects, data mining and data assimilation. I am going to use time series analysis again to be able to reinforce some of the basic thought process we have already discussed. This is an example of an explicit model. Here data mining step. What is the data mining step here? Given a time series, first compute and plot the Carlogram. And what is the Carlogram? Carlogram is the one that we already saw. I am going to give another example of a Carlogram. This is the time index k. This is row of k. So what does k refers to? K refers to the separation between two data sets, time t and time t plus k. How are the data at time t and time t plus k are associated with each other? For example, if I have a maximum temperature today, how is today's maximum temperature related to yesterday's maximum temperature? Day before yesterday's, 10 days ago. You can readily see today's maximum temperature may be related to yesterday's, but to a lesser degree day before yesterday, to a lesser degree to a week, almost no link to a month from today. So this correlation of maximum temperature, one can think of it like this. If you think of again unemployment percentage do not vary day by day, they vary over a period of a month. So today's unemployment is very much related to yesterday's unemployment. So what is the correlation between unemployment in time separated by 1 day, 1 month, 6 months, 1 year, where the basic units of time could be 1 day. So k refers to the number of days that separates two time epochs between which I am interested in correlation. So this is what is called a correlogram, plot of row of k versus k. Row of k is a correlation between data that are k steps apart. Then what is that we do? So this is data dependent. So this is created from a particular data. So this is some sort of a summary of what this data tells us. Then how do you utilize this? Mathematicians have helped to create several different types of models for time series analysis. These models are called ARIMA. AR for autoregressive, I for integrated, MA for moving. So it's like 3 different families of models. It's called AR model, integrated model, moving average model, ARIMA models. These ARIMA models are a very broad class of potential model that one can build. Mathematicians have helped us to be able to build all these models ahead of time, and they have analyzed the underlying correlation properties of each of these models and have cataloged. In fact, they have developed albums and albums of properties of correlations of various types of models. For example, an AR model could be an first order model, second order model. An MA model could be a first order model, second order model. An AR MA, first order AR, second order MA. So in general, one can have AR MA PQ. So P refers to the AR type, Q refers to the MA type. By changing P is an integer, Q is an integer. By changing P and Q, I can get a whole family of models. If each of these models are created, I can mathematically compute what their correlation should be, and I can plot these correlations and create an album. This album is the fundamental basis for almost all of time series analysis. How do I use this album? You have already cranked out the correlation for a specific data set. Then you visually compare the given picture, the photo, with the album that you already have. You narrow down which of the pictures in the album closely resemble the one that you have that depicts the particular data set you have, and that helps you to narrow down. Maybe it looks like AR 2 and 3. Maybe it is AR MA 1 1. You don't simply say this is it. You look at the things that are close, you narrow down the model to 2, 3, 4. Each order will have different kinds of parameterization. So use the same data to be able to estimate the various parameters of each of the models. And once you fit different models to the same data, then you can compute what's called the error in the forecast, the error in the model. Use that error to further select much more finely the appropriate model that could be used in this particular case. So the data assimilation step now, so the first one is analysis of data. Second one is comparison of the given data with the album. Once a particular data has been narrowed down, then you come back to the old step called the data assimilation step. Estimate the parameters of the different models using the same data set. So here I would like to emphasize the difference. In the process based models, models are created by the scientist, observations are created by measurement scientists. They don't talk to each other, but our job is to bring them together. So the model building and data assimilation part are separate, but in the case of empirical models, all you are given is only the data. Based on the data, you have to develop a model. Once you develop the model, you use the same data to be able to assimilate the data into the model. And again, model selection becomes an important situation in these cases. Here, comparing the album, I would like to bring an analogy here. All of us happen to go to the doctor once in a while. In order to understand what happens with your health, doctors order different kinds of observations on you, blood test, chest x-ray, maybe an MRI, or maybe other chemical analysis of your blood. Once a chemical analysis of the blood, x-ray, MRI, all the things are made available, a doctor hangs them all together and he or she looks at various signals that these observations provide us. Then they go to the anatomy book. The anatomy book describes what an ideal body should be. They compare the present situation with an ideal situation. Oh, this looks right, this looks right. Oh, this looks not that good. They try to narrow down a particular possibility and then do further steps, do further steps, do further steps. Once they understand, then they go for the treatment. So to label you have this disease, to label you have that disease, to label you have this problem, that's a prediction problem. To be able to predict, I need to analyze the model. And how do they use the model? They use the models are to them the anatomy textbook. So there is a data, there is an album, they compare the data with the album to be able to generate, to be able to make a forecast. Once the forecast is done with respect to medical diagnosis, forecast then leads to treatment and then recovery. In the case of hurricane forecast, we make a forecast, then we tell the public there's going to be a 20-inch rain tomorrow. Move people up to the higher grounds and so on and so forth. So the aim of data assimilation in general is to be able to fit models to data so that we can generate useful forecast, and the forecast can be used in many different ways for public consumption. So that's the overall underlying philosophy that we'll be pursuing in this course. So data mining and data assimilation, DM for data mining, DA for data assimilation. They are also used in machine learning. In this case, the models are implicit. We are not going to do much of machine learning in this class. We are not going to be doing much of time series in this class. That's why I would like to spend a little bit longer time to start with, to be able to see the other relations to data assimilation. So goal is to train a machine, say an artificial neural network, to classify samples into two classes. Given a set of, for example, medical diagnosis, for example, blood analysis. A blood chemist gives the blood chemistry. The whole idea is that, can you feed this blood chemistry information into a neural network? You train the neural network so well to be able to predict, yes, you have hepatitis A, no, you have hepatitis B, no, you have hepatitis C. 50 years ago, we did not know that there was a disease called hepatitis. Then they know that there is a disease called hepatitis. Then they found out hepatitis is not one kind, it's a multiple kind, A and B. Then they found out it's not A and B, there's also a C. Have we discovered all aspects of hepatitis? The answer is no. We never know. There could be C, D, E, F, G, H. So once you know that these are the characteristics of the blood that corresponds to A, B, C, we would like to be able to automate that decision process. So neural network is essentially a classificatory mechanism into which you feed this chemical information. It prints out the particular kind of disease that corresponds to that. That's a classification problem, typical classification problem. Another classification problem is, in a post office, I would like to be able to develop a machine that can read the addresses, to be able to sort them. Human can sort, but I would like to automate the sorting process by machines. So that's a pattern recognition process. But I write in a way different from yours. But the machine cannot handle all the ways of handwriting. So we are going to say, hey, if you want to be able to use the machine to classify, you have to type in a particular form. Once you have typed in a particular format, a machine can be taught to be able to classify the addresses in different groups. That's artificial network. Making this network do these processes is called learning phase. So given a set of samples and their associated classes, so what does that mean? These correspond to type A hepatitis, these correspond to type B hepatitis, these correspond to type 3C hepatitis. So there must be an expert who already knows a particular analysis, also the classification. He has labeled them. So once I have a sample with their associated classes, then what do? You divide the samples into two groups. One large subset called the training data, another small subset called the testing data. So we use the larger training data to be able to train the machine. That's called learning with the teacher. We always learn with the teacher. There are two kinds of learning with a teacher, learning without a teacher. In case of learning with a teacher, you learn by recognizing that you made a mistake. In the case of learning with a teacher, I already know for this input, this must be the output. I know for specific. So you can train using this data, the known classification, an artificial neural network to classify. So this is essentially a fitting process. In the learning, this is called the learning with the teacher. During this phase, I make sure on this data set, this machine behaves in the best possible way. Then I would like to understand whether the machine will be able to do things that it has not already seen. So if I use the same data that I use to teach and then certify, that's cheating. So I would like to be able to test it with the set of data that was not used in the training phase, and that's why we have talked about two subsets, a smaller subset. Now you feed the data set that the machine has not seen earlier. If on this data set the machine does very well, then you have succeeded in making the machine learn. Though this is from a higher angle, you can look at it as a data assimilation process. We are fitting the behavior of the network to suit the classifications of a given data set. So you can see machine learning and data assimilation have a very strong interconnection. Data mining and data assimilation in artificial neural network is an implicit model. Again, this is a quick summary of what I already described. The data mining phase. Here, what is the data mining phase? The choice of the structure of the neural network. I simply talked about neural network. How do I define the neural network? It has number of stages, number of neurons in a given stage, the total number of inputs, the total number of outputs. These essentially describe the topology of the underlying artificial neural network. This essentially comes from experience. This is the data mining phase. The mining relates to a lot of experience that one has. Should I have 2 layers? Should I have 1 layer? Should I have 5 layers? Should I have 1 output? Should I have 2 output? So these are all the decisions that an engineer has to make in the design of the networks. Once the network is designed, the structure of the network is designed, we are at the same level as in the ARMA case. I have picked the model. We are on the same level as I had picked a hurricane. I have picked the hurricane model. So the model is already fixed in here. The data assimilation phase is to fit the chosen structure to the training data by minimizing the error in classification. The testing phase is the prediction phase to see whether the artificial neural network handles the new situations very well. So you can see the data assimilation is intimately associated with learning. My own background, my PhD work was essentially in machine learning. That's why I could jump into data assimilation part rather easily. Data assimilation is the basis for any kind of learning mechanisms or learning devices. So different facts about DA all in one place now. DA can be looked at curve fitting. DA can be looked at estimation theory. DA can be looked at statistical regression. DA can also be looked at system identification, adaptive optimization. So looking at DA is like five blind men looking at an elephant. A person in curve fitting looks at curve fitting only. A person in science statistical regression looks at statistical regression only. Our job is to be able to bring the big elephant. This is what I was trying to tell in the very first slide. The sum is greater than the parts. The sum, the data assimilation. To further understand the richness of data assimilation, we need to introduce further classifications of both models and data. And that's what we are now going to look at. Until now, we classified models only at a broad angle, namely process based models or empirical models or data specific models. That's the classification at the highest topmost level. Now I need to bring down finer nuances into the classification. So models in general can be classified along different dimensions. A model can be static or dynamic. A model can be deterministic or stochastic. A model can be linear or it can be nonlinear. A model can be perfect or it can be imperfect. Almost all the models are imperfect. I don't think there is any model that is perfect except few. I am not saying there is non-existence. For example, the model that governs the motion of the planet Earth around the sun is very nearly perfect. Why? How do we know that? We are able to predict the lunar solar eclipse for the next 100 years. And sure enough, when we say there will be a lunar eclipse, lunar eclipse happens. But there are very few systems where we can make such accurate predictions. So perfect models are few, imperfect models are large. A model can operate in discrete time or in continuous time. A model can work in discrete space or in continuous space. A model can be finite dimensional or a model can be infinite dimensional. For example, a person working in static regression, he may be interested only in static deterministic linear nonlinear case. A person in system identification may be interested in dynamic deterministic models, linear nonlinear. A person working in time series analysis would be interested in dynamic, stochastic, linear, nonlinear, imperfect models that operate in discrete time. Most of the models in geophysical sciences, they work in continuous time and continuous space. If a model is given by partial differential equation, that is infinite dimensional in nature. If models are given by ODE, they are finite dimensional. So you can see data simulation looks at the entire domain of modeling with all its nuances, with all its abilities to classify models along these many different dimensions. And in our course, we are going to take such a global view. So what does it mean? With this course, you can do data simulation in several different walks. You can handle any kind of different models. So we are looking for the ultimate generality that underlie the notion of what data simulation, what models, and what is the holistic view of data simulation. That's our purpose. Examples: deterministic, dynamic, continuous time, infinite dimensional models. ODE, xt. So I am now going to introduce some notations. X is the state of a system. T is the continuous time. Rn is the set of all vectors of size n, real vectors of size n. When I say xt belongs to Rn, xt consists of n components. Each one of them are functions of time. Xn is considered the state of the system. For example, in a meteorological setup, what is the current temperature, pressure in downtown Bangalore? So time, midnight, midday, 8 o'clock. So what is the state? How do I describe the state of an atmospheric system? Temperature, pressure, humidity, wind speed, all these constitute different components of the vector, and that's called the state of the system. The model also can have a set of parameters alpha. There could be p number of them. We will use n to be the size of the vector which represents the state, p to be the size of the vector that represents the parameter. We will use alpha, the Greek letter for the parameter, the English x as our state. So what is the linear model? X dot is equal to ax. So this is a differential equation. X dot dx by dt, the rate of change of the system. A is a matrix, x is a vector, x dot is a vector. Matrix is real matrix of size n by n. It needs an initial condition x naught. So that's the ODE. Now PD, U, T is the time variable, x is a space variable. In the case of ODE, there is no space, only time. Phi is a function of x and y, that's essentially space, no time. So phi is a function of space but no time, two dimensional. U is a two dimensional, but one is time, another is space. A linear partial differential equation could be a Poisson's equation. Double derivative of phi with respect to x, the second derivative of phi with respect to y is equal to minus x comma y. It has to be solved under certain kind of boundary conditions. A standard nonlinear model is u t of x. The time derivative of x plus u times the space derivative of x must be 0. That's called the Burger's equation with a suitable initial or boundary condition. Oh gosh, I think there's a spelling error. It's called Burger's, B-U-R-G-E-R. Then there's an integral equation, f of x 0 to t, kx of t, m of t dt. Here f and k are given. Our job is to find m. So given k is called the kernel, f is called the forcing. My job is to be able to find m. So you can see models of deterministic, dynamic, continuous time, infinite dimensional can occur either as an ODE or a PDE or an integral equation. Examples of deterministic, dynamic, discrete time, infinite dimensional models. Replacing the time derivative with suitable discrete time approximation, I can express differential equation into a difference equation. By replacing an integral by a sum in the standard way that we do in numerical integration, we can get a variety of discrete time models. The integral equation gives rise to a linear equation ax is equal to b. A is known, b is known, my job is to find x. That's a static model. The dynamic model is xk plus 1 is equal to m times xk. There's a linear discrete time model, x naught is the initial condition. A nonlinear model, xk plus 1 is equal to m of xk alpha as a parameter. In this case, I have initial condition, I have parameters. So I am now giving life to a representation for different kinds of model that we talked about in general. Now I would like to bring the distinction between model state versus observables. Observables are related to quantities that I can observe directly. For example, vorticity, but I can't measure vorticity directly, it has to be measured indirectly. Volatility, the price changes, that is called volatility. Volatility is a quantity that affects us, but I can't measure it directly. So there are observables, but there are states. Not every state is observable. For example, if the observable is pressure, I can directly measure pressure. If the observable, if the state is a vorticity, I can't measure vorticity directly, I have to measure indirectly. So I would like to be able to relate the states of the model and what is being observed and relate them. So I would like to be able to bring the distinction between the two. Modeling, in spite of all the effort that have gone on for centuries, is still an art as well as a science. A modeler has full freedom, limited only by his or her imagination, to concoct newer relation between variables of various types. So the novelty in modeling relates to the ability, limited only by the imagination, to be able to describe various relations that underlie between quantities that describe the system. So here we can discuss the variables into two types: direct variables, derived variables. Direct variables are directly observable: pressure, temperature. Derived variables, the model needs a derived variable but is not directly observable. Examples: height, position, velocity, temperature, energy, stock prices, interest rate, unemployment. These are all direct variables which are directly observable. Vorticity, entropy, CAPE, volatility, inflation. Some of you may come from meteorological, geophysical sciences, but my interest comes from applied mathematics. To me, analysis of time series models in the financial setting is no different from analysis of time series models to analyze climate data. Underlying mathematics is the same. That is why I am trying to give a broader explanation of variables. So vorticity, entropy, CAPE. This is the convective available potential energy, which is very important in severe storms. Volatility is very fundamental to many things we do in life. For example, the current deluge in Madras, in Chennai, is because of a low pressure system that came and sat on the top of Madras, didn't move at all, and dumped. It is a very rare event. So if you look at the frequency of these events, if you look at the intensity of these events were high volatility. It's the effect was way too much. Same thing, inflation. Inflation was very high. When I went to United States in the late 70s, we had 14 or 15% interest rate. Today is close to 0. So inflation in those days was very high. Inflation, there's virtually none. Inflation affects everybody, but inflation is something that cannot be measured. It has to be inferred. So inflation is a derived variable. Volatility is a derived variable. Entropy is a derived variable. But my model may need these derived variables to be able to make analysis. So here I am going to talk about the relation between state variables and observables. Dynamics of sea surface temperature in equatorial Pacific, that is a state variable. This state variable is of fundamental interest in predicting El Nino. As we all know, we are in a very severe grip, we are under the very severe grip with El Nino, very strong. They say the average temperature is more than 3 to 4, very close to 4 degrees, and it is affecting weather in different parts of the world. Vorticity dynamics is another state variable for vorticity equation. The total water content in a cloud system, that's very much needed in cloud physics. Speed of a car in a cruise control. Today we are talking about driverless car. Google is developing driverless car. So I need to be able to measure the speed of a car very accurately to be able to feed back to the control element. All avionics, a flight starts from Bangalore airport at 2 a.m. goes to London in 8 hours. You cannot see anything. Everything is automated. So the autopilot has to be able to adjust the speed based on various measurements. So a plane has tons and tons of observables relating to the situation where it flies. The models of the dynamics is already programmed to the autopilot. So the autopilot model varies the various control devices based on the observations. Is there a headwind? Is there a tailwind? And so on and so forth. So to be able to control, I need to understand the state variables. It could be sea surface temperature, it could be vorticity dynamics, it could be total water content, it could be speed of a car in a cruise control. Observables. How do you measure the equatorial Pacific temperature 1,000 miles west of Hawaii? Nobody can go. It is very difficult to develop a network of buoy systems. So we have to measure the temperature essentially from satellites. Satellite measure only the thermal energy that was radiated in the infrared domain. So we have to estimate the temperature based on the thermal energy received by the satellite and invert using the very well known radiation physics laws, Stefan's law, Max Planck's law, and so on. What is the dynamics would use the observables are the prevailing wind, the UVW component from which you have to essentially compute the vorticity. The total water content in a cloud, there is no way to directly measure, it is measured through the reflectivity of the radar. The raindrops are hanging in the cloud. Once you send the beam, the radar beam, it gets reflected by the water droplets. So the intensity of the returned reflected beam is displayed in various colors, and we can estimate the amount of water that is inherent in the cloud by looking at the reflected energy. So that's the reflectivity is observable but is related to the state variable called total water content. Voltage generated, which is proportional to the speed, and that's what cruise control uses. You set the speed for 70. Because the road condition, if the speed comes to 68, the accelerator knows that there is a difference, it pushes the car forward. If the road is smooth, if you have set 70 and the current setting, it may go 72, it shuts off a little bit to be able to control. So I need to be able to measure the speed to be able to do a good cruise control. With the interest in driverless cars, this notion of models, observation, data assimilation becomes very fundamental to replace a driver by a computer, because we need to know the dynamics of the model. We need to know different road conditions. So a car is fitted with lots of observing devices, measuring devices. An onboard computer has to process all the devices almost instantaneously to be able to steer the car in the particular lane. And they have to they have attained a limited success in doing this. It's a long way to go, but it's an intellectually stimulating project where modeling, observations, bringing the models almost online to be able to use and to be able to steer. The decision there is to be able to steer. The decision methodology is to be able to predict. And so you can see the underlying aspects of data assimilation again coming along from different directions. Now I'd like to we talked a lot about the model. I have not talked much about the observations. So I'm now going to talk a little bit more about observation because it's one of the three key players in the system. Observations of physical variables such as temperature, pressure, wind are subject to measurement errors. These measurement errors are called noise. For example, what I may read as 2.5, you may say it is 2.3, one might say it's 2.6. So observational errors when humans measure certain things. Even instruments, if you look at any instrument, they will say the following. So if you buy an voltmeter, they will say, well, it can read from 0 to 100, the accuracy is 10%. What does it mean? If it says 60, it is plus or minus 10% of 60. And where the error comes in, the engineering aspect of the design of the instrument itself. So that's one way the error can come in. The other way the error can come in is, how do I calibrate? The meter shows 60. Is it really 60? We have to calibrate a meter against standards. So it could be design errors within, or design difference. There's no design error. There is a design differences. There are manufacturing differences. There is calibration differences. Then the human being able to read these, all these together lumped into one phase called measurement noise, or the measurement error. Following Gauss, one of the very well known mathematicians of all time, who lived between 1777 and 1855, he was the first one to be able to analyze the properties of observation noise. In fact, in his time, the only kinds of data that was available was measurements about very many celestial objects made by humans using very simple telescopes. That's all that they had. They had nothing else. So he was to be able to make sense out of these observations, and these observations were not consistent. These observations contained a lot of errors. So by analyzing a given set of observations, he modeled the statistical properties of the observation errors and developed the so-called bell curve. So what did he show? He showed the following. If this is 0, the errors form a bell-shaped curve. On an average, the error is 0, but on a given circumstance, the probability of an error could be either positive or negative. It took a bell-shaped curve. This is what's called the Gaussian curve, and we all know this curve is given by f of x is proportional to e to the power of minus x squared by 2. There is a constant of proportionality that comes into play. So this curve is a bell-shaped curve. Was one of the most fundamental contributions of Gauss is to be able to establish that observation noise essentially followed this bell-shaped curve, and we use this to this date, and that's a very enduring aspect of Gauss's discovery. So this kind of noise, it's also called the white noise. What does it mean? I measure the temperature today, I measure the temperature tomorrow, I measure the temperature day after tomorrow by the same instrument. The error today is not correlated with the error tomorrow, the error is not correlated with the error day after tomorrow. So there is no correlation. When sequences are not correlated, there is a particular way to characterize this, that's called white Gaussian noise. Gaussian refers to the bell-shaped curve, noise is the error, white means they are uncorrelated. White noise means errors are uncorrelated. These noise also have a known correlation structure. For example, if you buy a voltmeter, they say, hey, 10% accuracy, 15% accuracy, 20% accuracy. You can measure, you calibrate, and you can compute the error. So observation noise has to be associated with the error properties. The error properties have to be related to the known covariance structures of the errors. In economics, stock prices, the interest rate, foreign exchange rate, they are all intrinsically random. Pressure, temperature, there is a variability from night and day. That comes because of the phases of the day and night, the phases of the moon, summer, winter, autumn, spring. So these are all the variations induced by season, variations induced by the day and night. December 31st, the maximum temperature in downtown Bangalore this year, next year, over the past 100 years, if you plot them, there is a natural variability. So things could have natural variability, things could have underlying stochastic properties. So when we talk about random, the randomness can come from either from the noise or from intrinsically random variations. We will stop here at this moment. We will continue these topics in our next lecture. Thank you.